Honors Algebra 2 Pre-Calculus, and we're doing 2.7 in Algebra 2, which is technically called a preview of transformations, but we're going to go ahead and dive pretty in depth into what transformations look like. Even though your book calls it a preview, really this is going to give us a good overview of what we need to know about transformations moving forward. So let's talk about what transformations are. So if we memorize graphs of some basic parent functions, right? So these are functions that we're going to see a lot of that are really common graphs, like the square root of x or x squared or x cubed. We can use that knowledge and also the knowledge of these transformation rules that we're going to learn in 2.7 to anticipate what graphs of in that family would look like. So in that family of functions. So for instance, if you know what an x squared looks like, you can graph an x squared plus 3 pretty easily without actually graphing it. Now why, or like you can visualize the graph without actually graphing it. Now why is that useful? So remember that most of the skills that we build up in this course and in every course you've seen, you're using these skills to the ends that you hope to be able to solve long, complicated problems that will use these skills without being specifically requested. What I mean by that is, as you move forward in math, you're not going to be asked to graph a function like x squared plus 3 very often. You might have to do it in this chapter of this Algebra 2 class, but realistically, that's not a long-term skill, right? The long-term skill is that sometimes you're going to need to know what a graph looks like to answer other questions about a problem or to do other things in a problem. So you'll need to know visually what a graph looks like, but it'll be a total waste of your time to actually graph it. And if it's a calculator section, if a calculator is allowed, then obviously you could actually type and put it in your calculator. But my argument is that even that is much more time consuming than just being able to very quickly in your head visualize, oh, hey, this looks like this, right? So that's why we're going to try and get used to this transformation of function stuff. Now, if you choose to not learn this very well or to just learn it well enough to get through my test and then be like, cool, I knew it and now I don't know it and I don't care, that's all right. That's a choice. The difference is that people that are good at this skill set tend to be able to do problems more quickly or a certain sort of problems more quickly because they have this basic knowledge. Remember, the more knowledge you can accrue, the better, and then you can apply it in certain ways. Cleverness is applying the knowledge. Knowledge is the stuff that you actually memorize. Okay, so moving forward, let's go ahead and go to the next slide. Okay, so let's talk about some of the parent functions. So for right now, I'm actually only going to have you learn 4. But in the grand scheme of things, we're going to learn more than this, right? We're going to start with these 4, but in the grand scheme, we're going to learn exponential functions, logarithms, trigonometric functions, and eventually maybe some others. So let's start with x squared. So you can, I think most of us know what y equals x squared looks like, but if you were plotting the points, right, it would be, it would start at 0, 0, right, and then 1 squared is 1 and 2 squared is 4, right, and the same thing on the other side, negative 1 squared is 1, negative 2 squared is 4, so you get a parabola, and again, I apologize in advance for my inability to draw things on this apparatus very well, but you get the gist, okay, so that's what it looks like. Now, if you need to actually plug in those points to figure out the shape of a parabola, that's fine, but I'm going to suggest it's kind of worth memorizing, right? The square root of x, again, I'm going to plug in some points now, but realistically, I would hope that you're not plugging in points moving forward. So the square root of 0 is 0, the square root of 1 is 1, and the square root of 4, because 4 is a perfect square, is 2. So it looks like this, give or take. Again, I recognize that my drawing skills are terrible, but that's okay. I'm not actually going to be grading on your drawing skills. If the right points are there, I understand. X cubed, right? 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8, which is like somewhere way up here, right? Because here's 4, 5, 6, 7, 8. So way up here. So this is basically going way up really fast. And it's doing the same thing in the opposite direction, right? It's going to be a negative 1 cubed is a negative 1. And negative 2 cubed would be a negative 8. So it's dropping off pretty fast. In fact, so fast that I accidentally drew off the paper. Okay, cool. That's the basic idea. And then we talked about the absolute value of x in 2.6 when we talked about special functions. It's that v, right, that essentially looks like y equals x in this direction and y equals negative x in this direction. And again, I did a kind of terrible job of hitting those dots, but you get the idea. Okay, cool. So those are the 4 parent functions I'm going to ask you to know for this particular unit. Again, I'm not expecting that your ability to draw by hand is stellar. I'm already not a great grapher, and then I'll be honest, I'm way worse when I'm using this. So those are 4 that you want to commit to memory. You want to not have to think too hard. If somebody asks you, what's the graph of x squared, right? You want to just know that. All right, cool. So moving on. So we're going to learn 2 sort of big types of transformations. We're going to learn rigid transformations, which is what these are all going to fall into. And we're going to learn non-rigid transformations. What makes a transformation rigid, right? So what makes this rigid is that the shape stays the same. So uh, f of x keeps its exact shape. It's almost like, in fact, since I am using a computer to do this, I could actually like copy the shape and drag it to a different spot. It would still be exactly the same shape, okay? So rigid transformations are called translations, that's like sliding the graph up and down, or reflections, where you flip a graph over vertically. So the reason I color-coded these the way that I did is that changes made outside the function, and we're going to talk about this on the next slide, but you see how this minus k and this plus k and this negative sign, see how they're outside the function? Okay, so if the change is outside the function, right, if the change is outside, right, that's going to mean that it is vertical, meaning up and down, right, vertical, and 2, logical, right, meaning that plus is up, right, and minus is down, right? So vertical and logical. And so if you notice, plus k means go up k units. So see, it's vertical and it's logical. Plus k means up k units. Minus k means down k units. A minus in front of the f of x means flip vertically, meaning across the x-axis, right? And we're going to do examples of this in a minute. But in red, I have changes that were made inside the function. Okay, so changes that happen inside whatever my parent function is, right? Inside changes. See how this plus h is on the inside and the minus h is on the inside and that negative is on the inside of the f of x, right? Inside changes are horizontal, meaning left and right, and backwards, right? So they are horizontal and they are the reverse of what you'd expect. So what you'll notice here is that if I add an h on the inside of a function, normally we would think of plus being right, because on the axes to the right is positive. But remember, I said it would be backwards of your expectations. So that's a translation or a slide left h units. X minus h on the inside would move right h units, right? So again, outside changes, vertical and logical. Inside changes, horizontal and backwards. And we're going to walk through these in a little bit. All right. So before we go on to other changes, right? So we're gonna skip to another slide. In fact, I'm gonna skip the slide that I originally had next. Let's walk through example 1. Okay, so in example 1, I'm gonna graph the parent function f of x equals the square root of x, right? The reason I can tell that these go with that parent function is that they have a square root. Like, I'm not trying to be, like smart about it. I'm not trying to be snarky. If it has a something cubed, then my parent function is probably x cubed. If it has a something squared, my parent function is probably x squared. If it has an absolute value, my parent function is the absolute value, right? Okay, so let's graph the original first. So I know that the original should look something like these 4 points, and I'm going to do my best to graph it. Okay, that's not tragic. Okay, so root x plus 2. This plus 2 is outside the function, right? So this should mean up 2. Now the fancy official word is a translation, but you could say slide up 2. So basically what's happening is each one of these points I move up 2 units. Up 2, up 2, and that's my new function. Now I can label them f and g, but I was kind of lazy and color-coded them so that I wouldn't have to. So there's my g, which is the transformed function. And there's my f of x, which was the original, right? Now, because I'm using a computer program, I also totally could have just cheated, right? And I could just copy this and then drag it over and show you that if I take this thing and move it up 2, that's what it should look like. Now, again, I'm not doing a very good job at it because I clearly kind of stink at graphing, but you get the gist. So this is the parent function, and I move up 2 units, and look how it's a rigid transformation. It's the same shape. Again, assuming that I could graph better than I do, okay? And then if we want, I can actually, let's make that red so that it makes my point. Okay, cool. All right, so let's do the next one, right? So for my root x plus 3. So what I want you to notice here is that this plus 3 is on the inside. So that's going to mean that it's left or right because it's horizontal. So I'm going to slide, but I'm going to go the opposite direction you'd expect. So you would expect that a plus 3 would be positive, would be right, but that's not how it works. When it's horizontal, I'm going to slide left because I'm going to go the opposite of what you'd expect. So left 3 units. Okay, so if we go ahead and graph the original, Oh, actually, I'm going to be a lazy bum. Yep, definitely going to be lazy. Okay, hey, look, there's my original because I'm a lazy bum. Okay, so there's my original f of x, right? So if I graph that original f of x, right, the same way I did before, now what I'm doing, and you can see that I'm going to do this by hand first, but then I'll show you that if I drag it, it's going to be the same thing. I'm taking each one of these points and I'm moving left 3, right? So this point, I'm going to move left 3, and this point, I'm going to move left 3, and you're going to get a graph that looks like this. Okay, so that's going to be my h of x, right? And again, the black one was my f of x. Now, if I were to take and copy that thing that I already copied once, right, and drag it over, you'll see that sure enough, this black graph shifted to the left 3 units looks exactly like that. And again, I'm gonna go ahead and make it blue so that it matches what we're doing. Okay. And again, forgive me for being terrible at drawing. Okay, so that's what these look like. Now, if I go ahead and pull out a calculator to show you what this would look like on a calculator just to prove my point, right? So what I'm going to do is I'm going to put the square root, right? So I'm going to do second squared. So I'm going to square root of x. So my f is going to be the original function, right? And then down here, I'm going to do, let's go ahead and do a first. So I'm going to do second x squared x, right? And plus 2. Now what I'm going to do is I'm going to go over, hang on, I'm going to move this guy up. I'm going to go ahead and change this to the thicker line so you can see the difference. Now when I graph them, they should confirm my graph. And sure enough, you see the thin line is the original and the thick line is the red line. And sure enough, that confirms what you can see, right? If instead I went back to my y equals and I changed this guy to the x plus 3 parentheses, now you're going to see that this should match my graph that I have for part B, right? So again, just to show you, that's better. Okay, there you can see it. So just to show you that you can confirm this on a calculator, but it's a waste of time. Although I'm asking you to graph these now in this particular section so that you learn the skill, you're really not going to be graphing these by hand as you move forward in math very often. Okay, so what we're going to do next is I'm going to go ahead and take you to an E1, or a P1 rather, and I want you to try the same thing I did. Now here our parent function is an x squared, and you're going to do a transformation and you're going to write what transformation it is. And then we'll go from there. So you can go ahead and pause me if you want. I'm going to start by graphing the parent function for both of them, right? So my x squared function is a parabola that looks kind of like this, and I'm going to try really hard to get it in one motion so I can do that thing where I cheat. Oh, I missed. Oh, I missed. Hang on. I'm trying really hard to get it in a nice smooth motion so that I can do that thing where I cheat and copy it, but I failed miserably, so it's okay. All right, so we'll start it here. Close. Okay, boy, am I bad at drawing. Okay, so the points I should have are 2. Oh, I'm terrible at this. Okay. I quit. I'm not going to bother to try and get it in a smooth motion. So 0, 0, 1, 1, 2, 4. Same thing on the other side, right? Sorry, I'm getting used to this pen as we go. All right, that's as close as we're going to get it. We're going to call that our parent function, okay? Then we're going to do the same thing down here because I know I'm going to need it. And one of these days, guys, I'm going to get good at using this. But for right now, folks, you just got to put up with me. Okay, cool. It's supposed to be a U shape. But I guess this is good training for the fact that it's really hard to graph things by hand sometimes. Anyway, so there's my parent functions, right? So now let's go ahead and walk through what's happening here. So I noticed that this is a -1 on the inside. So since it's on the inside, it's definitely left and right. So I'm going to slide. But remember, the inside is the reverse of your expectations. So normally you would think -1 would be left, but because it's the reverse of my expectations, I'm going to go slide right 1. So basically, the bottom part of this parabola is going to slide to here, and then it's going to be exactly the same shape. And again, I didn't do a very good job drawing the shape the first time, so I don't know why we'd expect I do a good job this time. But oh, hey, that was slightly better. Cool. Until I did that. Okay, ignore the line part. Oh, well. Hey, you live and learn, man. We all get a little bit better at things as we work on them. Okay, so ignore that. All right. I think that it is not a shock to any of you that have met me in person to recognize that I am violently out of my comfort zone using this. All right, cool. So slide to the right 1. Again, the official word for slide is translation, and that's fine, but if you say slide, that's okay too. Now, here's the function, right, the squared. So that means that this change is happening outside. Outside changes are vertical and logical. So this is going to be a slide down 4. So basically, this U shape is just going to move, all the dots are going to move down 4. And I'm going to take the U shape and I'm going to try my best to draw a parabola. Hey, that was the best one yet. And that's basically the gist of how these transformations work. So as we progress, we're going to do some slightly harder versions. We're going to, in the next video, we'll combine multiple transformations in a single example. And then we're going to talk about some of the non-rigid transformations, which are definitely the ones that people find the hardest. So that's it for this video.